let's see. All right. I have to consent to being recorded. There we go. So any questions about this? So I know a number of you are really interested in that cumulative long-term stress. And for those of you who are interested in that kind of how cumulative stress exposure affects people's functioning, it might also be worth looking at, what is the mechanism here? And one of the mechanism potentially could be that cumulative stress actually affects acute stress responding as well. And certainly these aren't necessarily a one-to-one relationship. So when I'm talking about the autonomic nervous system, this is the automatic part of the central nervous system. A lot of you are going to remember this from way back in elementary school or middle school. So this is what regulates all of our body functions, our heart rate, blood pressure. And there's the two arms of the autonomic nervous system. There's the parasympathetic, which is that rest and digest arm. It's associated with relaxation, recovery, release of acetylcholine. The parasympathetic influence usually travels along the vagus nerve. So you'll often see this kind of sometimes measures of parasympathetic responses are also kind of measuring vagal tone or vagal influences. So this is you're relaxing, you're stimulating digestion, you're slowing your heart rate, increasing saliva production. And then the sympathetic arm, this is our fight or flight response. So this is where you're getting a dry mouth, dilated pupils, rapid heart rate. You're inhibiting digestion, increasing sweat, and stimulating adrenal medulla, adrenaline, noradrenaline, all of that. So usually what we're interested in, well, not only, but usually we're interested in part of that sympathetic response when we're talking about a response to stressors. The other thing we could be interested in is regulation of that response, which would tap more into that parasympathetic arm. So this is my adapted image from some of Ted Beauchene's work that describes an integrated model of the autonomic nervous system, in which he kind of conceptualizes motivational functioning as being mediated by the sympathetic nervous system, and regulation, as we talked about, as regulated by the parasympathetic nervous system. So I think there's a couple important things to note here. And he also kind of separates the motivational systems into kind of motivational approach or activation and motivational inhibition. And you can see that these are associated with, so you can see cardiac activity is interesting in that it's innervated by both sympathetic and parasympathetic fibers. So that's one of the reasons some of you have RSA or HRV. That's one of the reasons why we can look at heart rate and it can tell us so much. We can also look at electrodermal responding or skin conductance as a measure of behavioral inhibition, and also sympathetic functioning. But I think the important thing kind of in thinking about this at a person level is that the behavioral and emotional predispositions aren't directly predicted by any single system. So those dotted lines or dashed lines are just a schematic to demonstrate that really these are not direct associations. And it's worth kind of thinking about how there was this era of research where it was really the brain is the control center. And so, signals started in the brain and then went outward. And I think the past couple of decades of research has really discounted that, suggesting that other body systems are capable of generating, storing, responding to electrical activation patterns that in a similar way as the brain. And so it's not necessarily a brain forward system. One of the other reasons that I like to show this schematic is because it helps us to make sense a little bit and conceptualize why we might see different patterns depending on which sympathetic measure we're looking at. So for instance, if we're looking at some sympathetic aspect of cardiac activity, that may not map directly onto electrodermal functioning. And Ted Beauchene suggests that that's because that skin conductance element really is tapping into more of this behavioral inhibition piece. I'm realizing that it is hard for me to see all of you and the slides at the same time. So what I'll ask is if you have a specific question or comment or something that you'd like to add to the discussion, please go ahead and unmute yourself and go ahead and shout out, or you could type it into the chat if you're a little bit shy. That would be fine too.
I have a question.
Yeah.
I might be having lots of questions because this like seriously focuses on my research. And I want to find out, per your experience, how accurate have these measures been with cardiac activity, like heart rate and electrodermal? Because I was building my my design, I was thinking, should I go with just the heart rate or should I go with skin conductance? Like, I'm not really sure. But the tech industry is still growing, so they really don't have an accurate measure of a skin conductance, but they do, with the heart rate. So that's like a question, for you.
That is a good question. So anytime people ask about validity of these measures, I get very nervous because, I mean, they're objective measures, so they're valid measures of what they are.
Mm-hmm.
Are they valid measures of emotion?
No.
That's debatable. Are they very noisy because there's individual differences in bodies? Absolutely.
Yeah.
So I will definitely kind of share my personal experience with which ones I find to give the most consistent or reliable findings.
Great.
Unfortunately for you, because you're interested in wearables, I will tell you, if you're interested specifically in sympathetic responding, I have personally found electrodermal responses to provide me the most kind of reliable data.
Wow. Okay.
So in terms of measuring acute emotional responses, in terms of it behaving in the way that I would expect it to behave.
Wow.
If you're looking at sympathetic activity, heart rate is it's innervated by too many different things, sympathetic and parasympathetic. We see deceleration if people are calm, but we also see deceleration if people are interested. Exactly. And so it's really messy to try and interpret heart rate.
Okay, great. Okay.
Sorry, I know that's not the best news for you.
No, that's fine because I'm at the design stage, so this really helps.
Okay, so we'll go a little bit into cardiac activity, and again, it's not to say that it's not going to tell you something important. It really depends on your research question and your paradigm. And this is something that, I remember I went to an EEG training with Steve Luck. Some of you may have gone to one of those. And it really just like resonated for me, like how much of this isn't about your measures. It's about your paradigm and your question. And so a lot of the interpretability of the data rests entirely on your research design. So I'll talk a little bit about these markers, but that's why I'm thinking it could be useful to do a little bit of, sitting down and thinking through, like, how can you develop a paradigm that might leverage these to their best advantage. Okay, so again, this is just kind of a little bit of high school biology or middle school biology. So again, the heart is innervated by both sympathetic and parasympathetic system. And so that means that, and obviously activation of the former is going to lead to a relative increase in heart rate, and activation of the latter is going to lead to a relative decrease. And so what that means when we're talking about heartbeat, this is what we're kind of picking up, are the electrical signals. So I'll just kind of walk you through this. So the heartbeat cycle each has its own kind of pattern of electrical signals. So we have diastole, when all 4 chambers are relaxed and blood is kind of passively just entering. Then we have contraction of the left atrium and right atrium. So our atrial kick that causes blood to enter the ventricles. And then at a certain point, you're going to have pressure in the ventricles is greater than in the atria. So the valves will close, hopefully, and blood won't backflow into the atrium. So that's our, oh, I think I'm behind us. And then we have our ventricles contract, which opens the outflow valves so blood can go into the pulmonary or systemic system. And then the pressure will, of course, decrease and the valves will close again. So this is just every heartbeat. And what that maps onto are the electrical pathways in the heart. So the heart is really special because it has its own sinoatrial node, that its own pacemaker. So it's actually firing action potential. So this doesn't really happen in other areas where it's kind of, this is why well, this is an old reference, but for those of you who remember Indiana Jones in the Temple of Doom, and he's holding the heart and it's beating, it's because it's beating on its own. And it fires an action potential 60 to 80 times a minute spontaneously. And that firing rate is your heart rate, and it's going to change with the changing needs of the situation. And then it's regulated by the autonomic nervous system. So it's initiating that an atrial contraction. And it can slow down or speed up depending on what our parasympathetic and sympathetic systems are telling it. So we can think about the action potentials in the heart. When we're looking at an electrocardiogram, it's the average of all of these action potentials. So when a group of cells depolarizes, we're going to see this chain reaction where the rest of the heart is going to depolarize unless there's, still in the refractory period. So you can see at these different labeled time points, at 0, the sodium channels are opening up, potassium channels are closing. At 1, we see the sodium channels are closing. And there's many other channels, but this is essentially to say this is how it maps onto our electrocardiogram, so that we have these different points in the standard ECG. And so you'll see your P wave, which is theoretically at the atrial depolarization. You see your QRS complex, which is at the ventricular depolarization. And then the T wave at the ventricular repolarization. So when you're seeing that decrease in voltage back to resting state. So this is what you will be seeing when you're taking any kind of heart rate or cardiac measure. And some of you are probably very familiar with how to obtain these data. But I'm going to present in BIOPAC because that's mostly what I have used and what I have found has the best customer service. And so essentially we just pick, depending on your system, depending on if you have any other grounds, you pick a triangle around the heart. And I have some videos where I can show you how we've selected hookup. There are setups where you can put electrodes on kind of ankles or on arms. I don't recommend that if you have people who are going to be potentially moving or writing or doing a task during data collection. So all of this, I'm guessing, is review for many of you. Any specific questions before we motor along? And please go ahead and shout out, because I'm definitely not going to see you all at the same time. I'm guessing there's no question. All right. All right, so we're going to keep on rolling. So a couple of you have mentioned RSA or HRV. And so this is often one of the measures that we're interested in gleaning from cardiac data. So this is this heart rate variability is the kind of reflects that interplay between the sympathetic and parasympathetic system. There's a number of different conceptualizations about what HRV is about. It's often regarded as a measure of autonomic flexibility, or maybe even a biomarker of emotional responding or emotion regulation. So it's been proposed that HRV reflects the level of inhibitory control of the prefrontal cortex. It's also been proposed that this at baseline measures capacity to regulate emotions. Usually when we're talking about heart rate variability, we're not just talking about the variability in that beat to beat. We're not just talking about that beat to beat variability in length, but we're usually talking about one specific aspect of heart rate variability that taps mostly into the parasympathetic system. So I'll talk a little bit about the different ways you can get to measures of that. For those of you who are more familiar with the term respiratory sinus arrhythmia, it's essentially that same thing, that element of heart rate variability that we think is attributable to parasympathetic activation, right? So we know that over a respiration cycle, there's variability in heart rate, right? Anytime we inhale, our heart speeds up. Anytime we exhale, our heart slows down a little bit. And so we can think about that respiratory sinus arrhythmia in much the same way. There are a number of different theories that aren't necessarily competing with one another about what HRV is all about, but they emphasize different things. I will just highlight that some of these theories really are focusing more on kind of developmental or evolutionary origins, and the empirical support is maybe sparse. So the neurovisceral integration theory really focuses on the connection between the prefrontal cortex and heart through the vagus nerve. And so really conceptualizes HRV as one way of measuring capacity to adjust to environmental demands, where higher vagal tone would be associated with better cognitive and emotional performance, or better stress response kind of capacity. The polyvagal theory really focuses on vagal tone as potentially evolutionarily associated with social functioning and helping us to modulate our response to stress so that we can engage effectively in social situations. And here again, higher vagal tone is considered associated with better social functioning. There's the biobehavioral model where vagal tone is supposed to, kind of regulate that exchange between respiratory and cardiovascular processes. Again, higher vagal tone reflects better functional energy reserves. Some other kind of overlapping models, a resonance frequency model focuses on how we can actually increase our vagal tone through things like paced breathing. Similarly, psychophysiological coherence model really focuses again on how we can use paced breathing and alter our vagal tone directly. So there's a couple of things to highlight with all of these. Most of these theories really focus on hypothesizing how baseline HRV might be related to overall psychosocial functioning or socio-emotional functioning. What it doesn't necessarily speak to is what phasic shifts in HRV are all about. And that's in part because the meaning of a phasic shift in HRV, so when I talk about phasic shift, that means that's what a lot of us might be interested in if we're measuring acute stress. We're looking at that reactivity, the change that happens in response to that exposure to a stress. And partly that's because what that change means depends on what the stressor is and what the environmental demands on the individual are. So this is where it all comes down to your design and what you are asking of your participant in that moment. We can generally kind of talk about HRV as something that, you know, at baseline, we want kind of higher resting levels of, that would be more optimal to functioning. And then we would also expect that in response to experiences of negative emotion, we should see a decrease or vagal withdrawal. On the other hand, if we think people should be regulating their emotions, we might want to see an increase. So you could have a stressor, and if you want that person to be able to, if you want the person to be able to sit and notice the negative emotions, you might actually want to see a decrease. That might be optimal. If, on the other hand, you want the person to be regulating their emotions in order to do some sort of task or something, you might want to see an increase. And so when you're talking about trajectories of HRV, it really depends specifically on the stressor and the paradigm and the tasks that are incumbent on the participant. So we can talk a little bit more about that later on. But I just wanted to kind of make sure that you all have that now. There's multiple different ways that we can parameterize HRV. We can look at the amount of variability with time domain analyses, and we could also look at the types of rhythms that are contributing to variability with frequency domain analyses. And we can there are multiple pathways to get to the question that you might be interested in. So I'm assuming that if we're looking at HRV in the context of stress, you're probably mostly interested in that vagal influenced component. And so in terms of the time domain, we can look at the root mean square of successive differences in those and intervals. Usually this is in milliseconds, or the percentage of successive differences that are greater than a certain threshold. And again, this is thought to capture most of the parasympathetic influences. And that's because the faster cycles are most likely vagal mediated, right? So those faster shifts in heart rate variability. So we can kind of break down heart rate variability into kind of the very low frequency, the low frequency. There's also high frequency. There's also very high frequency. Nobody really looks at this unless you're looking at infants. And the high frequency domain, which is greater than anything, it's about 15 cycles a minute, but anything greater than 10 cycles a minute would correspond kind of with respiratory frequencies, and is that vagally influenced aspect that's mediated by acetylcholine, and more immediately affects the SA node. So those are the fluctuations that we're most interested in. In terms of cycles a minute, we can think of those sinusoidal waves of how many complete cycles are occurring per minute. The slower fluctuations, those that are less than about 10 cycles a minute, we can think of as both sympathetic and parasympathetically mediated. So of course we can do our kind of Fourier transform to turn from the time domain into kind of decomposing each waveform into its respective kind of sinusoidal waveforms and look at different frequencies and map them onto how much power is in each frequency domain for a particular epoch of time. So that would be the alternative to the time domain analyses. And you all have probably used both of these if you've used HRV before, or at least familiar with them. So I mentioned RSA again. So those are the rhythmic oscillations in heart rate that are produced by respiration. And so again, magnitude of RSA is considered an index of parasympathetically mediated HRV. So if you're looking in the literature and you're like, what's the difference between RSA and HRV? Oftentimes we're talking about vaguely mediated HRV. So we're talking about similar paths to the same construct. I've already alluded to this interpretation piece. Let's see, chat, make sure I don't miss it. All right. So let's see. So again, we talked a little bit about tonic or kind of resting HRV. Higher is usually considered beneficial. But those phasic shifts requires a little bit more interpretation and consideration of the paradigm. So a higher level of vagal withdrawal or a decrease in HRV may be adaptive if we want the individual facing a stressor to actually be able to sit with the emotion, to notice that emotion. It demonstrates the individual's ability to provide the organism with necessary energy to face the stressor. But if we want that individual to be able to engage in, I don't know, executive functioning tasks or something in the context, then higher levels of vagal withdrawal might actually be problematic because they may not be able to address other tasks. There was a recent study that actually suggests that tonic HRV may influence phasic HRV, which of course makes perfect sense, that where people are at influences the meaning of those shifts. Any questions so far? For those of you who are already using HRV or have used HRV or RSA in your work, does this map onto your own interpretation or your own data?
I'm definitely not one of those people, but I have a question.
Yes.
So I've never worked with HRV at all, but I'm just curious, I think you kind of alluded to this at the beginning, but how do you see chronic stress? Do you see chronic stress affecting the tonic HRV and also the phasic? Or like, how do you think about that?
Well, so I think of stress as external. And these are measures of internal processes. So, so I will just kind of separate those into two pieces, right? So somebody's stress response may not always directly map onto their stress, right? A couple of you have actually are studying exactly that. You're looking at like what moderates in terms of like psychosocial resources or that kind of thing. What moderates that relation? You have some people who are exposed to cumulative stressors and have this maybe resilience or something. So I will just to be really clear. So how would stress exposure affect these different domains? Well, you might expect somebody who's chronically stressed to have fewer kind of less regulatory capacity. Like I'm assuming that person is pretty tapped out. And maybe by virtue of their environment, they're not getting a lot of support. So I might expect lower levels of tonic responses. Depending on what the acute stressor is, they might be very practiced at responding to acute stressors, or they may not have the capacity to mount a response to those acute stressors. So I would expect probably depending on the prolonged stressor, that there might be some change in terms of phasic responses. So I'm most familiar with people who are dealing with psychopathology, but let's be real, when I'm talking about psychopathology, I'm really talking about people who have oftentimes chronic traumatic exposure and that kind of thing. So I do think about living with psychopathology as one form of chronic stress. And so certainly in those populations, we see some alterations in how quickly people are able to mount a response. We see maybe that that the trajectories over time don't look quite as promising, like they're not quite as able to mount a long-term regulatory response in response to an acute stressor. But most of the changes most consistently are about baseline levels. I don't know if that answers your question, Emma.
Yeah, thank you.
Okay, so I actually have some data just to give you an example of what some of the correlations between these measures and measures of emotions and their respective kind of self-reported measures might look like. So one study looked at resting HRV and found that it did consistently was associated with self-reported difficulties in emotion regulation on the difficulties in emotion regulation scale. So again, that's resting HRV, that's that tonic measure. And it predicts faster safety learning. So safety learning is basically this idea that you can learn danger, right? So if I expose you to a specific image and I have like a really loud noise that I pair with it, you might learn that that image is dangerous, right? And so we can think about that as similar to how trauma or fear learning happens, or how people learn to be like on guard or hypervigilant in somewhat dangerous situations, right? Or situations that are surrounded by threat. But we also want people to be able to learn safety, right? And they need to be able to differentiate safety from danger. And so the ability that resting HRV is associated with faster safety learning, about being able to kind of pull apart, okay, well, this picture is associated with a loud noise, but this picture isn't. I think in this case, that's what it was. I think it was, they looked at bursts of sound. Oh, and they might have looked at, yeah, they looked at skin conductance as well. But so that's one way to think about how chronic stress and acute stress might be associated with at least resting HRV. That resting HRV might suggest more difficulties regulating emotions and less ability to learn safety. I'm also just kind of presenting, this is just an overall summary. And this is by no means a systematic review. This was just my best, grasp of the literature. So in general, lower HRV in terms of resting HRV is associated with psychopathology across a number of different disorders. We also are more likely to see vagal withdrawal in response to laboratory stressors. So, so that decrease in parasympathetic functioning in response to usually a negative emotion cue in the laboratory. So I haven't directly said this, and I know people do it all the time, but I don't love using heart rate as a measure of emotional responses or stress response, because it is innervated by both sympathetic and parasympathetic processes. And so the interpretability of it's tricky, right? Because if people are paying attention really closely, their heart rate's going to go down, but if they're upset, it's going to go up. But if you're upset, probably paying attention. So it's really hard to know what to make of it. One way of tapping into more sympathetic processes on the heart is focusing on cardiac pre-ejection period. So this is the time between the left ventricular depolarization and the ejection of the blood into the aorta. And so shorter basically means more sympathetic response. So we can think of it similar to kind of a more rapid heart rate, but a little bit more of a specific measure. The problem with PEP is you need more than just ECG to measure it. That's really the issue here. So PEP shortening is supposed to mark dopaminergic reactivity. And this is kind of like mobilizing the body to meet environmental demands. So basically very consistent with sympathetic responding generally. So what we need to obtain this data is really we have to be able to measure impedance, the kind of slowing of the electrical impulses through the heart, depending on how much blood is basically in there. So measuring PEP is a little bit sensitive because you're measuring impedance, and that's just a little bit more of a sensitive measure. It's a little bit harder to get clean data. If you're using a BIOPAC system, usually you need an entirely separate module in order to measure this in addition to ECG. But you would usually use 2 electrodes up here and then 2 electrodes lower on your back. So this isn't just, I guess I will take a moment to talk about just arousal generally. I probably should have mentioned this earlier on. So a lot of the time when you're interested in stress, we're talking about negative stress, and we're talking about a negative emotional response. So far, all we've been talking about is arousal, right? And sympathetic arousal is not valenced. It's not, positive or negative. So when we're measuring PEP, that sympathetic activity is both associated with probably fear responding, but also associated with approach behaviors, like when you're really excited by the prospect of earning money on something, right? And this is the case with all autonomic responses. Like these are not valenced. I do have one kind of not directly autonomic measure that you could supplement to try and get more valence, but we'll talk about that a little bit later on. I'm not going to go much into detail except to say I don't really totally understand how impedance is directly measured. I used to have to do this by hand and measure kind of distance between the change in kind of the B wave on the ECG waveform and essentially kind of like where you would expect that fluid volume to shift in the heart rate when we're talking about that blood flow. And that's really what we're measuring. We're base impedance is reflecting static tissues, muscle, bone, resistance to electrical input. And then we have that dynamic fluid volume that, and that's the one we're interested in. So we end up looking at a derivative. And typically that pre-ejection period is someplace between 0.05 and 0.12 seconds. So just to give you a sense of what this has been associated with in the literature. So this is just one study that looked at different kind of emotional film clips. And with recovery in between. So they had this was obviously a little bit of an older study. So scary film clips were like, I know what you did last summer. You can see that with that fear film clip, we see those rapid kind of shortening of PEP. So, so that's significantly different than the other film clips. the thing that I think is important to see here is that there is a significant difference between fear and sadness. And so a lot of the time when we're talking about stress, what are we talking about? We're talking about prolonged exposure to some sort of external event or quick exposure to something stressful, right? But which emotion is being evoked in response to that stressful event can dramatically alter your physiological profile. So I do think that it's important to kind of think about who are your participants, what is the specific stressor that you're really interested in. A lot of the time we think of stress as something that is really kind of fear-provoking or anxiety-provoking, but I think at a certain point, cumulative stress, maybe it's more about kind of hopelessness and sadness. And so, and that might be an individual difference variable. So this is something just to really carefully consider with your population. Perhaps one of my favorite, this is the old school way of measuring sympathetic activity. And in my own personal work, this has helped me quite a bit by providing pretty reliable measures that act in ways that I expect they should often. So electrodermal activities, same thing as skin conductance, galvanic skin response. Again, widespread neural underpinnings and not specific to the stress response. And again, it's reflecting autonomic arousal, not valence. And we're just measuring basically the fact that sweaty skin is more conductive and people sweat when they're excited and upset. That's all we're measuring. So we get 2 points. Often we're kind of looking at the fingers, mid-phalangeal, distal phalangeal, probably fine if you pick 2. If you're doing a task, you might want to pick their non-dominant hand so that they have their other hand to use. And then we have and typically EDA is measured in terms of microsiemens. So again, we can think about this in terms of tonic level and also phasic shifts, right? So there's a number of different parameters we can look at. We can look at the amplitude, the peak of that phasic response from somebody's own personal baseline. If you have discrete, specific like images or really kind of time sensitive marked stimuli that you're providing to people, you could look at the time to the onset of that event-related skin conductance response. A skin conductance response is considered any response that's over 0.05 microsiemens. And usually, so this is the interesting thing about skin conductance and also, the downfall, is that skin conductance response is going to happen 1 to 3 seconds after the event. So you can't kind of present a rapid series of images like you could in an MRI or with EEG because they're just not as precisely time linked. And you want to know which stimulus is associated with which response. So if you're trying to do skin conductance plus MRI or skin conductance plus EEG, you're really going to have to slow your paradigm down quite a bit. You might look at the number of skin conductance responses during a particular period. You could look at how swiftly that skin conductance increases. It's probably just worth knowing that there are, a subset of people, maybe like 15 to 20% of people who are non-responders in terms of skin conductance. Theoretically, that doesn't mean you can't get skin conductance levels, but it does mean that the meaning of skin conductance responses for those individuals is going to be different. typically we see lower levels of skin conductance in mood disorders and psychopathy, and greater reactivity is associated with aggression. This is just an example of how we can look at this and across different kinds of stimuli. So this basically looked at EDA across skin conductance and a couple of other different response parameters of skin conductance across different types of external stimuli. So all of the stimuli evoked EDA responses, but with different magnitudes depending on the stimulus types. So it's just worth kind of thinking, depending on your measure, which is going to evoke the largest magnitude response. So noises produced, I would say, the largest responses in this case, whereas images were much smaller. It's also worth knowing like how big a response breath has. So clearly people have to sit pretty still during these measures. So this is just a study looking at a whole bunch of different video clips. So negative, positive, and neutral. That, and people looked at skin conductance overall. And there was a significant effect of well, hang on, I'll just stop here so you can kind of see what these were. So I think it's important to know that there was a significant effect of arousal irrespective of valence. So both negative and positive film clips differed from the neutral clips. So again, we're picking up here arousal, not valence. So taken together, we can kind of generally distinguish between different emotional stressors based on profiles of autonomic nervous system responses. So we see those high arousal, we're more likely to see higher, this actually should be shorter PEP, so decreases in PEP, increases in skin conductance responses, and decreases in heart rate variability. And then with those lower arousal, sometimes we see increases in skin conductance responses. Sometimes we'll see an increase in heart rate variability. And there's been varied findings in terms of positive and negative low arousal emotions in terms of the effects on HRV. So questions about these so far? I know we're kind of, so these are all different ways that you can kind of mark acute responses to stressors. So we talked about skin conductance, we talked about both pre-ejection period and heart rate variability as measures of cardiac functioning. One thing that so let's see, at this point, let me see if I can unshare my screen so I can see more of you. So we've got about 10 minutes before our break. So at this point, I kind of wanted to check in and see where you are at. Oh, I'm sorry, we're 5 minutes past our break. Are we? No, let's see. Yes, we are. So we'll extend the break by 5 minutes, don't worry. But at this point, before you take off, I would love to hear from you if you are interested in either one, smaller work groups where you can kind of connect with people who might be doing similar research and brainstorm which of these measures you could use. 2, whether you want to kind of do a large group discussion, or 3, I have some additional videos about how to do hookup and slides that just talk about kind of general troubleshooting with collecting some of these measures. So those are the options for you for the second half. So why don't you go ahead and take your break from now? We'll start, since we're starting 5 minutes late, we'll go until 10:35 for the break. And if you could shoot out your preference, so whether you want to do some more slides and troubleshooting. So number 1 is small group discussions, 2 is large group discussion, and 3 is some more slides and talking through some troubleshooting and how to do hookup. All right, we will do number 3 loud and clear. Thank you all. Enjoy your break. So I appreciate that about you. One thing I did not ask you is how many of you actually want to see a video of how to do the hookup of like where to put electrodes? Would that be helpful? Would that not be helpful? Okay. My students were super helpful and made the video for me. There is one error that I saw in the video that I will stop and correct for you all. So we'll keep going. We'll take a little video break, and then I'll try and save some time for specific questions today too. I have a whole boatload of other slides that BioPAC sent me that I think it may have varied level of utility depending on who you are and what you're doing. Okay, so I'm going to go ahead and share with you. I have a little bit more information. And so this really is not what I said I would talk about, but I wanted to tell you anyway, because I'm really excited about this. So one of the downsides of what we've talked about, I mean, obviously, is the fact that arousal is not necessarily valenced, right? And so one of the things you might be wondering is, well, what kind of markers can I use that are objective markers that I could use to complement some of these more arousal focused measures? So I'm just going to put this out there. Electromyography is one useful complement. There's a couple of ways that you can use EMG. I've used it in the past to look at facial expressions. I would argue that I think that the utility of facial expressions really depends on your specific paradigm and your population, right? So there's a lot of people, especially those who have been subjected to chronic stress, who have learned to mask their facial expressions. And so you might find that concordance between specific kind of frowning and smiling muscles are going to be different. If you have space in your paradigm and you're really interested in looking at individual differences or condition differences in valence, then I really have grown fond of using the affect modulated startle paradigm, and we can use EMG here to measure eye blink response. So some of you have probably already used this paradigm or are familiar with it, but I'll just kind of briefly walk you through what this is. So here we can look at eye blink, literally just putting 2 little electrodes under the eye, pretty close to the eye, pretty close, to measure the magnitude of somebody's blink response. And this just leverages the fact that if you hear a loud noise and you're kind of just like hanging out in your hammock in the summer, you're going to have a pretty small response if you're not doing anything. It's a little bit bigger than if you're laying in a hammock and just really calm. And then if you're watching a scary movie by yourself and you hear that same loud noise and it's dark, you're going to have a much larger blink response. So there's this nice linear association that really maps clearly onto valence. And so if you're really trying to pick up on valence, this could be a useful complement. It does require its own kind of paradigm, but there are different variations on this paradigm that you can use. So this is one way to get that kind of biological marker, if that's something that you're interested in. You want that multimodal kind of assessment, and you want to have some sort of marker that complements your focus on arousal. This is one option for you. So I'm just going to present some data that I'm really interested in, because this is similar to a paradigm that I'm using, where the stimuli in this case were pleasant or neutral or unpleasant words. And so participants with borderline personality disorder were presented with a series of these words. Some of these words were accompanied by a startle blast. So that's like a white noise sound. And you can kind of look at the size of that blink response, both across unpleasant and neutral words, but also across individuals. And so you can see in this case that individuals with BPD had a much larger startle response than people without BPD. And when they got that blast in conjunction with the unpleasant words. So this kind of paradigm, I'll just give you an example of how I'm using it in one study. So I have a small study where we're looking at emotional functioning before and after an intervention among people who are suicidal and have borderline personality disorder. You'll see that this paradigm is a little bit more complicated, because in this paradigm, I'm also looking at response to a novel and repeated images as kind of a measure of habituation to repeated exposure to an image. So there's a couple of things here that I just want to highlight for you. So one, the intertrial intervals are very long, and that's because I'm looking both at skin conductance and EMG. And so I mentioned a little bit just in passing that skin conductance response lags quite a bit. The onset of that skin conductance response can happen 1 to 3 seconds after exposure to the stimulus. And so if you're using multiple measures, it's really important to build your paradigm around the longest acting measure to reduce interference across trials. So the upside is I have multiple trials. I can look at responses to negative and neutral images. I can look at responses to novel images and images that they're seeing again. But I don't know if you all can hear the screaming that's happening downstairs, but that's my 2-year-old. I'm super sorry. Can you quiet the boy? Sorry. Working from home. He's not listening. Okay, so anyway, so I just wanted to kind of show you some of the things that come into play when you're building a paradigm with multiple measures. All right, so and so with this specific paradigm, what I'm doing is I'm choosing some of these images that are going to have startle probes alongside them. You might consider having different timings for the startle probes, because there might be a difference between whether it happens right initially with the image or later on. You also don't want people to like all of a sudden feel safe, like, oh, phew, this one doesn't have a startle probe. So it's useful to have some variability here. Okay, so that's just one thing that I wanted to share with you, that if you're really curious about how to complement this focus on arousal, you're interested in Valence, what can you do? And then I've pulled together some of the kind of major considerations and issues in this area. I will just say the big picture is that a lot of the time, your psychophys measures are not going to match your self-report. And so it's really important for you to kind of know ahead of time how you're going to interpret differences there. It's worth it's worth taking a moment to look at some of the literature on response coherence and see if maybe your population has one of those factors or one of the factors that might moderate coherence across kind of response domains might be relevant to your particular sample. So I know there's some research looking, this is my area is emotion regulation. So there's some research to suggest that maybe emotion suppression might decrease coherence across different response domains. Another issue that might be relevant in your sample might not be. So is considering other kind of psychological variables. So in looking at, for example, PTSD and skin conductance responses, or no, actually that study was cortisol. I looked at cortisol reactivity and really needed to control for dissociation, and found that dissociation really mattered. Same thing with PTSD and BPD. So if you had both of them together, that actually kind of reduced some of the coherence a little bit, where BPD was associated with people saying, I'm really upset and having greater skin conductance reactivity. But if PTSD was on board, it kind of reduced that connection between cortisol reactivity and their self-report. So there's a number of different, and so if we think about, PTSD as really a good example of somebody whose stress response system is out of whack, that might be something that would be important for you all to consider if you're dealing with a population that's under chronic stress. Other big picture issues that aren't on this list are that these measures are very noisy. There's a lot of individual difference variables in terms of body size, how comfortable people are with having you sit there and put sensors on them. So there might be times when your experimenters are kind of just getting by and not adjusting more, because if they kept adjusting or trying to fix things, you would have somebody walk out of the room. And so, there comes a time when you may need to make the decision between bad data or no data. So those are kind of the more kind of big picture considerations. Some of the more kind of nuanced questions, I alluded to this much earlier, is looking at HRV and respiration. There's been a long debate as to whether we should be controlling for respiration. I will say, I usually measure respiration and examine it and look at kind of correlations. I've actually never found that respiration is strongly correlated with HRV in my samples. So it's useful, I think, to monitor it, to consider what your protocol or what your decision making is going to be about whether or not to control for it. Coupling is likely to differ across individuals. Some paradigms do a paced breathing to try and get everybody on the same breathing page, and then measuring HRV from there. Depending on what you're measuring, but especially if you're interested in stress reactivity, I think you're actually going to rob yourself of a lot of variance if you do that, potentially. And it's conceivable to me that actually respiration is one of the mechanisms by which HRV actually means something. So I recommend monitoring respiration. So collect those data. If you're gonna do some paced breathing to get people on the same page, really carefully consider and make sure that that's not gonna rob you of the variance that you're actually interested in. And then across all of these measures, I'm going to strongly recommend that you use within subject designs. And there's a couple of kind of technical reasons for doing that, but mostly because it's so noisy and there's so many differences that the best thing that you can do is have a paradigm that is set up that you can control for some sort of baseline state. And that way differences between conditions within a person are actually, you can measure them across people. there's a lot of potential confounds. So one of the things that is really important to consider is room temperature. At UMass, this has been a major issue. I have a temperature controlled room that is controlled by something outside of my ability or anybody's understanding. And so definitely like really carefully consider room temperature. If you're measuring something like skin conductance and you really care about how sweaty people get, then you really just can't have everybody baking in a 90-degree room. Other things that are really important to think about are medications. Do you want to exclude people who are on medications? Which medications matter? Unfortunately, there's not a lot of good reason to use dose as a really sensitive way of measuring medication because, you know, people build tolerance, different doses in different bodies mean different things. So ultimately, you're probably going to have to measure medication in a dichotomous way. But you might do that across classes of medication, those that are likely to have a stronger influence than others. But even things like hormonal contraception and SSRIs are likely to affect some of these measures. I cannot exclude people based on their hormonal contraception or psychotropic medication. So, I mean, this is just really a conundrum, and this is another reason to be really designing your study, if you can, so that a within subject change is meaningful and interpretable in some way. There's other things that are a little bit more possible for you to control. So like nicotine use or caffeine use or eating recently or fasting, right? So with a lot of these peripheral measures, you actually don't want people to abstain from caffeine altogether if they're heavy caffeine drinkers. That's going to be a recipe for non-normal responding. Same thing with cigarettes. So you might come up with a threshold, usually, you know, an hour for cigarettes, 2 hours for caffeine or something like that, where they've had what they need and then they come in, do the paradigm. If you can avoid things that are kind of PRNs, certainly you don't want people taking a bunch of benzos during, or even worse, in the middle of your study, which has definitely happened to me. So really carefully measuring all of those things and coming up with some protocols. It's important to know how you're conceptualizing these different measures. What constructs are you thinking you're measuring? Does you know, how are you complementing this one marker? Which again, I would caution around. I know NIH loves talking about biomarkers. But it's hard for any of these truly to be a singular marker. So really consider, how are you multimodally assessing this? And does your paradigm cooperate with you? You want to be careful that some of your responses aren't specific to a particular stimulus. So, you know, certainly like you don't want to use like a visual stimulus for one condition and then, you know, an auditory stimulus for another, for example, right? Like you don't want to have, you know, watching colors on the screen for one and which I've done, and then listening to things for another, in the absence of having some clear kind of ways of controlling for that. If you can make sure that you have, if you are doing an emotion induction, you might consider multiple stimuli to make sure it's not specific to one set of stimuli. Let's see here. Other things that might be important to consider. So there can be some people who have kind of the tendency to respond within a single system across sessions, regardless of what the specific contexts are. So this would, so response stereotypy. So that's would argue for kind of having multiple assessments within a person and looking at kind of within person shifts. We've already talked a little bit about the law of initial values. So this is essentially saying the direction of response of a body function to any agent depends in a large degree on the initial level of that function. And that is basically to say, and I think that we can kind of see this in the data when we look at people with psychopathology and their skin conductance responses. So typically people with higher levels of psychopathology have lower levels of skin conductance responses and more skin conductance, or lower skin conductance levels, but more skin conductance responses. So we can think about them as kind of, they're closer to the floor, and so it's easier to get a departure from that floor. And the same we can think about in terms of HRV. We know that that kind of tonic resting level of HRV actually moderates how easily and what the meaning is of those departures from that baseline. So that is to say that we might expect, and we might even hypothesize and build our hypotheses around the fact that we think probably that tonic levels of a measure are going to moderate phasic shifts on that measure. It's useful to consider kind of practically what are sources of artifacts. Movement is a big one. If you're working with kids, you're going to have a different set of measures that you're able to use reliably than if you're working with adults. You know, just really practically, like if you're measuring some of these things, don't give people a chair with wheels on the bottom. Don't have them sitting in a chair with wheels. Just get a chair with just legs that sit on the ground. Otherwise, you're asking for trouble. You're going to have people monitor throughout and make sure that any movement is tagged, and really think about whether you want to remove physiological responses that are associated with movement from your data. And then it is really important to think about the fact that there is drift across the session. So those electrodes are sitting on somebody's skin. People are getting warmer, things are happening. And so there is going to be that within person drift over the session. This is especially obvious with something like EDA, where, you know, the absolute value you're going to see at the end of the session is going to be dramatically different than at the beginning of the session. So you're going to have to do some adjustments for offset if you're going to compare absolute values, or perhaps more easily, I know I've just said this in response to literally everything, like within subject comparisons are really, really helpful here. Some of these kind of phasic measures, we can think about skin conductance responses as essentially like a within subject comparison, right? Because it's looking at departures from somebody's own baseline. So I have had better luck, I would say, with using SCRs for that reason. So, and then I have a gajillion references. So I do have a video for you guys, and then I have some kind of more basic, you know, hardware related kind of items we can chat about. But any questions at this point before we show our video? No? All right. So we'll see how well this video works. Hopefully it's fine. If not, somebody tell me, please. Don't like make me have you suffering watching this video if it's not working. Because I can also just upload this to your folder for you so you can watch it at your leisure. All right. Oh, I'll just introduce them first. Let's see if I can. So this is Will and Lauren. So Will is on, I think, your left. And they were my lab coordinator, now social work student. And Lauren was my grad student, but is actually this month starting internship at Brown. So, all right.
All right, so today we're going to be demonstrating how to hook up a participant for data collection with psychophysiological data. So first you want to make sure that your MP150 is turned on and that you've prepared all of the necessary materials that you'll need for data collection. So for us, that includes this data transponder for collecting ECG and RSP or respiration data. That would also include the lead or the long wires connecting to the transponder, as well as the ECG electrodes. We will also be collecting some EDA or hand sweat data, so we need the transponder for that, as well as the leads, which will be shorter wires, as well as the electrodes for the hands. We also have 2 different gels, which may be necessary to put on the electrodes if they're becoming dry. So there's one gel for the EDI electrodes, as well as one gel for the ECG electrodes. So first we're going to get started by plugging in the leads into the transponder. So we're going to plug in the ECG in the proper place here, as well as the EDA. And you want to make sure that both transponders are on, and you can do that by checking, making sure that the light is flashing, indicating that the power is on. So we're going to start off by attaching the respiration band to our participant. So you want to make sure that the band is going around the sternum, and we're going to start off by having the buckle placed in the center of the sternum. So I'll ask you to hold that in the center, and then we're going to wrap the band around your body and filter it through the buckle. So we always want to make sure to keep the buckle in the center of the sternum. And you want the band to be relatively tight. You should be able to fit 1 finger underneath the band comfortably, and 2 fingers should be a bit tight. So how does that feel?
Pretty good.
Right there. Okay. All right. You'll also want to be sure to let your participants know that in order to make sure that the data comes in clearly, you'll want them to be wearing relatively thin clothing. So no big sweaters in the wintertime, no unitards, because we'll need to get the electrode on the actual rib itself. So you'll just want to warn participants ahead of time about appropriate attire. So next we're going to go ahead and start placing the electrodes. So specifically we'll need 3 of the ECG electrodes placed throughout the torso. The first one is going to go directly on the right bottom part of the rib. So I'll ask you to identify that bony part of the rib, and then I'm going to give you this electrode, and you're welcome to step off screen and place the electrode directly on the bone or as close as possible. All right, so next we're going to place 2 more electrodes on each of the collarbones. So you want to make sure to place it as close to the center of the collarbone as possible. So I'm just going to feel around for that. And then we'll place the other. All right. So now that we have the 3 electrodes placed appropriately, we're going to go ahead and attach the lead wires to the appropriate electrode. So reaching in over here, what we want to do is connect the white lead to the left collarbone. And you want to make sure that the wire part of the lead is attached to the electrode and not sticking up the other way. You want to make sure that's on pretty tightly. Then you'll attach the black lead to the right collarbone. And then finally, I will let you go ahead, if you can, and attach the red lead to the right rib.
So this is where I'm just going to make a slight correction. So you want it to be not on the bone, but right below the bone. So, but almost perfect. It'll still probably work, but yeah.
All right, so that setup is all ready to go, and we're going to go ahead and prep for the EDA data collection. So which is your non-dominant hand?
Left.
Left, okay. So I'm going to go ahead and attach the data transponder as if it's a watch, and you want to make sure.
So what you'll want to make sure to do ahead of time is have people wash their hands before they come in. Ideally not with cold water. Some people, if it's really cold in the winter, you're going to actually have to have them use warm water, warm up their hands somehow. This measure will not work particularly well if you have really, really cold hands. And one thing that you're not seeing here is that we usually will apply additional electrode gel to each of the electrodes. I'll talk about why, because even though these are disposable pre-gelled electrodes, they're not all equally gelled, and when you receive them, they're not still gelled all the time. And so you want to make sure as much as you can that you're having kind of uniform amounts of gel across of these. And then usually we'll use like a little wipe or non-alcohol kind of based wipe that to ensure stickiness. We don't do a lot of skin prep except for EMG. We will use skin prep for EMG because otherwise those data are pretty messy. But otherwise we kind of try to balance not harassing our participants too much. And so we try and get away with what we can, especially given the sample that I work with. So yeah, we'll keep watching for a few more minutes.
That the center piece is facing upwards in the center of the wrist. You also want to make sure that the leads are coming out towards the center of the hand as opposed to the opposite way. All right, so next we're going to attach the electrodes. For these, we find that the data comes in much smoother if we do use a little gel. So I'm just going to add some of that. You only need a small drop right on the center of the sticky part. All right. So we are going to attach electrodes to both the middle finger as well as the ring finger. And we're going to be using the distal phalange, which is the part of the finger closest to the nail. So you want to just wrap it around. And same for the ring finger. All right, so we're then going to attach just one of the lead wires, so the black one, to the middle finger. And until we calibrate, we're going to hold off on connecting the red lead. All right, so I'm going to move this over so we can take a look at how the data is coming in. All right, so I'm going to go ahead and we have Acknowledge open, which is the software we use for data collection. And I'm going to press start. So this little window pops up, which is asking me to do some calibration. So I'm going to click OK. Calibrate. And then I'm going to go ahead and connect the red lead to the participant's ring finger and press continue. All right, so I'm going to attempt to zoom in a little bit more so you can see the data more clearly. All right, and you want to make sure to have your participants stay as still as possible and try not to move the materials too much. So you'll see up top in this first row here, we have the respiration data coming in relatively smoothly. The middle row, we have the ECG data coming in, so you can see the nice QRS complex there. And then at the bottom, we have the EDA, or the hand sweat data coming in as well.
Okay, so there's your demo video, courtesy of Will and Lauren. Let's see, any questions about that? Some of you are probably very familiar with this.
So just a quick question. Is the participant standing up, or what position are we having the participant in?
So
Yeah.
they were demonstrating that standing because I have a very small lab.
Yeah, no, I get it.
But yeah, usually I actually do have participants stand when we're applying sensors. So that specific set was the Bionomatics line from BioPAC. So you probably noticed a couple things about that there's actually there's no lead that goes from, they're wearing their hardware, right? Or well, some of their hardware, they're wearing the transponders. So it's not truly a wearable situation, right? They have to be within, I think, 20 feet of the MP100 or MP150 or MP250, whatever it is now, system that is receiving the data. But there's a couple of reasons that you might consider using Bionomatics if you're going with BioPAC. One, if you have a bunch of lines going directly from the person to them, you are dealing with longer lines, you have more potential for line noise. And you also have potential for ground loops. In fact, you're certain to have ground loops. So you're going to have a slight offset in some of your measures. You're not going to be able to use all of the grounds. Whereas that doesn't happen when they're kind of wearing them. And it just gives them a little bit more freedom to walk around. It also allows you potentially, if you were going to do like a dyadic interaction, you could have two people kind of facing each other, not facing a computer screen, and kind of be able to move a little bit. But yeah, I do usually have people stand when I'm placing sensors.
Any other, so a lot of the work that I did in my postdoc was around TMS, and we did EMG and that sort of thing. And we had this whole protocol around removing watches, metal, all of that stuff, leaving cell phones outside of the room, things like that. But I don't know if that causes any noise.
I mean, we end up doing a lot of filtering to remove some noise. The cell phones are minor compared to the fact that there's actually 3 computers in that room.
Yeah.
That's really the issue. I usually deal with pretty robust signals. It's not like EEG or something where it's like pretty sensitive and pretty small signals that you're getting kind of through multiple layers. So like an ECG, you know, you could grab an ECG kind of like QRS complex wherever you are, however you are, upside down in the middle of like an electrical, like magnetic storm, probably. So it really depends on your measures. So I'm a little bit lax. I do have them remove jewelry or things that are likely to actually catch on leads or interfere with electrode placement. But aside from that, I have not noticed any issues. I used to be a lot more rigid about that. But the equipment's better, and I've just learned a little bit about the robustness of these particular. I just don't think it matters as much.
Okay, perfect. Thank you.
Don't tell BioPAC or you know, the super hardcore psychophys people, but this is why you're talking to me, the not super hardcore psychophys person. That's like, mostly I have to say, like, I work with people with borderline personality disorder who are really exquisitely sensitive, dealing with a lot of stress in their lives. Like, I'm not trying to have my study be the thing that stresses them out that day. And so I try and make it not as burdensome for them.
Could I ask a question?
Yes.
Okay. So, just do you use EMF detector? I found out that the lab space that I have, that there's a lot of noise and there's multiple utilities underneath, electrical wiring, a bunch of different things, and so the levels are pretty high. So I'm sort of thinking that through with respect to EEG, and so just to be clear, so that would be something that I would need to be concerned about with BIOPAC, but not as much.
I mean, it depends on your measure, right? Like if you're doing EEG, you need to be concerned. If you're looking at ECG, less so.
Right. Okay. And then the heart rate, vagal tone.
Heart rate variability, I think less so, right? Because that's derived from your ECG signal. So, so some of these measures are just a little bit more robust and less. You know, the downside of a lot of these is that you don't have that time precision element, like skin conductance responses. You're not going to get that response for 2 to 3 seconds.
Right.
So it's like the opposite of EEG in many ways.
Okay.
So yeah. So, but if you know there's a lot of noise, I mean, you can use get one of the super expensive shielded little.
Or find another room.
Yeah. I mean, I can't tell you how many rooms I've tried to find that are truly temperature controlled at UMass, and it's been a journey.
Yeah. Thank you.
I would be more concerned about temperature than I would about electromagnetic interference, I guess is what I'll say.
Right. So being able to run the air conditioner, but so they don't have too much sweat, but then also not as much noise. So.
And you want to think about when are you running the AC, like probably before they come in, and then turn it off when it's at the right temperature.
Yeah.
You don't want to be drying that sweat up as it's being created.
Right. Yeah.
What other kind of general questions? I do have some more slides if you want to see more slides. More specifics on working with BioPAC, which I'm most familiar with. I've also worked with Mindwear. I've worked with some wearables that were like the predecessor of the Fitbit, because it was back in, before times. Maybe, what was it, 2010 or so, where we used some like ActaWatch type of data collection. I will say the HRV that I got from that was very, very, very messy. So before you choose a wearable, take a look at how you're going to get the data. And it was just quite messy. We ended up having a lot of missingness. I guess that's something that I really haven't talked about, is that that there are times when an electrode will fall off or lose contact with skin, and so kind of setting up your paradigm so you have times to check in if there's specific stimuli that you can't present again or you can't start over, then be prepared for different patterns of missing this at different time points. Let's see. Yeah, so you want people to, I guess one thing is kind of informing people ahead of time. So my students mentioned a couple things. So you want to make sure that they're wearing things that actually allow you to access where you want to place those sensors. You also want to tell them not, especially we're using facial EMG to get a startle right now. So, I mean, people really can't be wearing makeup or they have to be prepared that like, we're going to be removing it in an area and they might need to reapply. So letting them know ahead of time. Same thing with lotions. We don't really want lotions. You want to make sure you're asking about caffeine, stimulants, alcohol, psychotropic medication. If you're doing facial EMG, you do want them to remove kind of any like chains or earrings that they would be wearing. So that's in terms of kind of prep. In terms of just before the participant even comes in the room, and as you're designing your paradigm, it's also really useful to kind of think through, how am I going to analyze these data? What is my specific paradigm? How much does time matter to my paradigm? So I have some studies where time matters barely at all. I have this like kind of story that unfolds and gets really upsetting, but it's across like 5 minutes. And so anything that happens in that 5-minute period is kind of fair game. And so I can look at kind of averages across that time. But there's other paradigms where you might be looking at multiple trials of different kinds of stimuli, and time really matters. Certainly with something like skin conductance response, hopefully time doesn't matter too much, because that is a very long lag between your stimulus presentation and when you're actually going to get the signal of the marker that you might care about. So you want to be designing those really carefully in mind with whatever your markers are. But there's also the possibility that you're going to have a lag in terms of when that actual response happens and when your computer sees it. And so it's worth actually considering measuring that lag if time is something you really care about. Like if you're simultaneously doing MRI or EEG, and time precision really, really matters, you are going to want to measure that lag somehow. I literally know people who have like photo detectors taped on their screen so that they can measure when the stimulus gets presented and then when they see it in their data set. So you can kind of do a workaround like that if you want to figure that out. Let's see, other things that people might really, really care about. Skin prep matters a lot for some things, somewhat less so for other things, but usually EMG is pretty sensitive. So you need to prep the skin. You're going to use a slight scrub, get something dainty like a tiny little Q-tip if you're going to do startle, because that's really close to the eye. If you have participants who are pretty patient, then I recommend using skin prep regardless. You're going to get a better signal and you're going to have less troubleshooting. If your participants are not patient, things like ECG generally don't require too much skin prep. Let's see. And usually I will ask people if they feel comfortable with, the specific gender of the experimenter that will be hooking them up. With COVID, we've been doing a lot of like trying to give people instructions and having them place their own sensors. That certainly, I'm not sure. I think it might be slightly more comfortable for participants initially, but it definitely adds time to the procedures and adds inaccuracy. I mentioned briefly that not everybody is a skin conductance responder. So if you're using skin conductance, you probably want to actually have some sort of stimulus, either a clap or tell them to take a really big inhale. And you want to see if you see that robust skin conductance response and track that so you know how many people are responders versus non-responders. Let's see, other things that people care about. Making sure you're using the, you might want to do some checks on your gain. So there's different ways of like testing things before you get going. We talked about calibration. Let's see. What questions do you all have? If you haven't done this before, work really closely with whoever is the provider for your hardware. So they'll often help you set up in the software a template to make sure that you've got everything that you want. And so you can do some calculation right online if you want to create some calculation channels to actually calculate some of the measures you're interested in. But beware of doing too much online calculation. You can do a lot of it offline and it'll bog you down, and depending on your computer speed, you don't want to have everything freeze up as you're in the middle of data collection. And I've mentioned BIOPAC a couple times, partly because they're very helpful. They're very easy to work with. They have great tech support, and they provide a lot of application notes for exactly how to score different measures and what experts in the field say in terms of interpretation of those measures. That said, like, it's all over the board and people often disagree about interpretation and scoring. So review the controversies and pick your side ahead of data collection, ideally. I think that's kind of mostly what I wanted to go through. Yeah. Any final questions, comments, queries, criticisms, compliments? All right. Thank you for hanging in there and tolerating the toddler noise. And I know yesterday was a very long and very, very heavy learning day. So I appreciate you all being here. We're going to wrap up and give you an extra 2 minutes. And you all have my email address. So if you have, ever any questions, I'm always happy to chat and share my own learning. All right. Have a good one, all.
A couple things I wanted to note is that the slides again are in the chat. If you missed that, you can click on that link and you'll see my slides. They are, for the most part, what you will see here. There are a few slides that I've taken out. I've said if there's any photos of people, I usually take those out, or if there's any drawings that a colleague has done, I might take those out too. But for the most part, they'll follow what we see today. The other thing is I won't be able to, all right, Amanda, we have a request to repost. So if you can do that, that would be great. The other thing is I won't be able to see you if you have a question. If you have any questions along the way, go ahead and post them in the chat. I'll do the best I can to answer them as they come up. And if there's a delay, you can post it again, or you can just shout out. That's fine. This is a pretty informal conversation. So what I'm going to do now is I will share my slides. I'm going to give you a little introduction into who I am and what we do in my lab. And then we'll take it from there. Okay, so I run the Nutrition Assessment Laboratory at UMass Amherst. This is a study team that I had a couple of years ago. Essentially, I have from 4 to 13 people in my lab at any one time. There's a little bit fewer people in the lab right now because of COVID-19. We really are interested in diet and physical activity on health benefits and health outcomes during periods of transition. And what I mean by periods of transition is there something psychologically or metabolically going on? So we look at adolescents as they come onto a college campus. We have the UMass Healthy Campus Study. We collected it when they were freshmen, and we followed them for 4 years to see how their diet and physical activity impacted their stress and sleep, and then we do some lipid profiles and inflammation in that group. We're interested in menopausal women. So as women go through menopause, they have a metabolic change that puts them at greater risk for heart disease. We know that the loss of estrogen increases disease of heart attacks and other CVD risk factors, largely because estrogen is an anti-inflammatory. So it's a naturally occurring anti-inflammatory, and we're really curious about how that impacts their overall health. And then we do some work in older adults as well, along the same lines. And I'll show you some data from each of those groups. Okay, so this is how this session will run. I'll talk mostly about inflammation biomarkers, an overview of the stress pathways, an introduction to some specific biomarkers. I'm going to talk about the 3 main ones that we see over and over again, but any biomarker that you're going to look at, these are things that you want to take into consideration. So as you go through these biomarkers, they're examples, but they're questions that you want to ask yourself as you select the biomarkers you want to use. And then we'll talk about the advantages of inflammation indices and scores. I think we're trending more and more that way to at least look at more than one inflammation biomarker. Because of the complicated pathway, it gives you more information to really hone into what your findings mean. We're going to take a little bit of a break, and then we're going to introduce you to the mesoscale discovery, which is a processing unit that allows you to look at multiple inflammation markers at one time. And then we'll also talk about data from the MST. All right, so metabolic pathways and inflammation. This should be fairly familiar to you. This is talking about the stress experience and what happens physiologically in the body when there is a stressor. This could be a chronic stressor or an acute stressor, but when there's stress on the body system, what we know is that it impacts heart rate, it's going to impact the cortisol levels, it impacts blood pressure. We will talk a little bit about coagulation activity because that's the work that I do postmenopausal women, but we'll focus, most of the talk will be focused on these cytokines. Why are we interested in this stress response? We know that it has big impacts on the physiology within the body around cardiovascular disease. It also has impacts on that trajectory. So if we think about metabolic syndrome, or we think about how that leads to diabetes, and diabetes leads to heart disease, these are kind of the intermediary factors that we think a lot about in my lab. And then it goes on to having disease outcomes, detrimental morbidity or mortality. So this is probably the most studied inflammation pathway, the NF-kappa B, which is a signaling pathway. And this slide just shows how complex it is. There's a lot of attention to blocking things in this pathway. TNF-alpha is often targeted in a lot of the animal models. If we knock out TNF-alpha, what are the responses that we have in the body? Can we decrease cancer risk, for example, because it's part of a cancer pathway? What I want to draw your attention to again is really looking at these cytokines, and then what happens once that cytokine initiation starts, and what the cascade effect is from there. Okay, so we're honing down into smaller and smaller pieces of the picture here. We are going to look at specific cytokines and inflammation markers that you may have heard about before. These are all important. And what I want to do in this slide is talk about, there are pro-inflammatory cytokines. The two that we're going to look at are TNF-alpha and IL-6. There are also anti-inflammatory cytokines. We won't discuss those, but they work, as you can imagine, either inducing more inflammation or reducing inflammation. One thing we want to note here is that TNF-alpha and IL-6 also have anti-inflammatory properties. That complicates the story that we tell with the data that we get. It's not that they become useless, but I think it's something that you're definitely going to want to note when you look at any biomarker. Okay, how much of it is inflammatory? Where do we see the pro-inflammatory effects? And then how do we distinguish that from anti-inflammatory effects? The other note that I will talk about, especially with CRP, that's the other biomarker that we're going to look at. Cytokines are initiated and then they impact the production of what are known as acute phase reactants. As much as you get into inflammation, you might want to know more and more about those things, but I think it's good enough to say that that they have different actions in the body. And then with CRP and some of the other biomarkers, they also help with tissue repair. So there's three actions that we want to think about when we're talking about inflammatory biomarkers. Is it in a pro-inflammatory state? Is it in an anti-inflammatory state? And is it in a tissue repair state? With those three things in mind, they will all be higher levels of these cytokines or acute phase reactants within the body. So why did we even get interested in inflammatory biomarkers? And we have a long history. It started in the 80s. I'll go through a little bit about that. But what we found were that some of the measures to predict cardiovascular disease weren't working as well as we hoped. So for example, blood pressure, there were errors within people. So some people would have high blood pressure in the evenings, but not at night. Or they might, if you've gone to a doctor's office, that sometimes they will take, and you're at risk, sometimes they will take it lying down or sitting up. So there became this situation where we weren't able to predict cardiovascular risk as well with some of the more common measures. And that was also true with some of the lipid profiles here, that they were inconsistent to stressors, whether they're acute or chronic stressors. So another reason why we decided to really start looking at inflammation biomarkers was there's something called allostatic load, which I think that you've been introduced to previously. And it's really kind of a number of different neuroendocrine markers like cortisol, there's metabolic markers, and there's cardiovascular risk markers, but inflammation, the immune markers, seem to be a better predictor of all-cause mortality compared to some of the other predictors. So that brought us here to inflammation. So there is, this is a graphic that I made, and we're going to spend just a little bit of time here thinking about whether a stressor is an acute stressor or it's a chronic stressor, and how do we get to this state of chronic inflammation. So stressors could be a number of different things. We've all experienced stress in one form or another. In injury, if you cut your finger, if there's infection, if there's bacteria or another pathogen. So what happens when you cut your finger? It will get red, it will get hot. Inflammation is Latin for starting fire. That's what it actually means. And so we'll get that reaction within the finger itself. Usually we get rid of whatever is the infection is. It resolves the inflammation and we go back to homeostasis. And this level of homeostasis is having a certain basic level of functioning. And this is kind of in the green or the blue, is adaptive healing. We can get chronic inflammation if there's unresolved acute inflammation. So there's a bacterial infection that hasn't been resolved, or this is the one I use all the time, is if you do not floss your teeth, you have chronic inflammation. We know that the bacterial and the teeth are related to heart disease, and not getting rid of that bacteria will actually have an unresolved acute inflammation that leads to chronic inflammation. Is it that much of a risk factor for heart disease? Some people will say yes, some people will say no, but that's how kind of these acute inflammations can get into unresolved acute inflammation to chronic inflammation. Some of the other more prominent stressors are kind of these long-term exposures to pollution. It's either exposure to a smoker, or if you smoke yourself. There is poor diet. We know there's an anti-inflammatory diet that's been kind of put around, or just eating foods that are higher in sugar, higher in fat, will have a direct impact on the body's inflammation. They also could lead to obesity, which is a chronic stressor. A lot of inflammatory biomarkers, especially that visceral adiposity, that stuff in the central adiposity, the belly fat, is a source of these inflammation biomarkers that really lead to disease risk, more so than fat in other parts of the body. We have this chronic inflammation, and that it leads to an increased production in these inflammatory mediators and immune response. And again, that leads to tissue damage, alternative cell signaling, activation of inflammation that we just can't get rid of. And it leads to both mental and physical disease. So depression is associated with inflammation, but so are the cardiovascular diseases and metabolic issues we spoke about earlier. Any questions about this slide before we move on? This is kind of the, all right. All right, so today, for the purposes of this talk, what we're really going to be focusing on are the 3 common biomarkers. CRP is probably the one that was the first one that was kind of looked at in any great detail, and its relationship to cardiovascular disease. There's interleukin-6, and then there's TNF-alpha. We'll focus on those 3 biomarkers. I'm going to talk about 2 simple inflammatory indices, and then we're going to talk about these cluster of adhesion molecules. And I really think that this last set that we're talking about, the cluster of adhesion molecules, it's found in the endothelium, and it's related to heart disease. Looking at those clusters by biological function is a place that has been largely unexplored, but has, I think, a really big potential for impacting how we understand inflammation on disease risk. Okay, so C-reactive protein is, as I said, something that has probably been looked at the longest. It is a non-specific biomarker. I'm going to give a little caveat here. We're going to talk about these things in broad brushstrokes but they have, as you will see, and as I will point out, it's not as clean cut as I'm presenting it here. So what I mean by that is CRP is often looked at as later down in the inflammatory cascade. So we had the central point when we were talking about the NF-kappa B cells and how that interacts within the diagram that I showed you, that very central piece. And then it kind of cascades where it hits the cytokines. And then the cytokines create those acute, the APRs, acute protein response and reactants. And those CRP is one of the things that happens later on. So it's really produced in the liver in response to other inflammatory cytokines. IL-6 will kick this cascade off, and then CRP will appear. Why is that important? It's important because where it is in that inflammatory cascade matters about when you will actually see its appearance. When you'll see its appearance and when you can test for it. And then this is the assesses the APH axis. When we see a lot of CRP, we believe that the stress has been activated, and it's strongly associated with cardiovascular disease risk and other outcomes related to CVD. Myocardial infarction, stroke, that sort of thing. So I'm just going to show you a little bit about CRP in one study of prenatal maternal depression. So when there was a group plant that did a study looking at if a mother is depressed during pregnancy, during the 20 to 36 weeks of pregnancy, their question was, what is the effect on the offspring? There's been a lot of work that's looked at what is the impact of diet on offspring. There's a Barker's hypothesis that says early exposures have disease risk outcomes later on. So if there was starvation, like in the Dutch famine or something like that, we know that the offspring of the mothers who were starving, they have poorer health outcomes, mental and physical health outcomes, cardiovascular disease in particular. Plant was interested in, well, if the mothers are depressed during this time frame, what are the long-term impacts on the children? So the basic level here is mother depression, but when we look at child malnutrition and we look at adulthood depression, that's in the offspring. So these two outcomes are looking within the offspring. And what you see here is that with those children that had maternal depression, they were at higher risk for having high sensitivity CRP, so higher risk for stress. And also when there was offspring malnutrition, they also had higher risk of a stress biomarker CRP. When we look at adulthood depression, when the offspring was depressed, they had higher risk of CRP compared to no exposure or no adult depression. They also were at higher risk than if the offspring was only depressed, and if the prenatal depression and adulthood depression were together. So this really is just looking at the interaction effects of childhood maltreatment and the effect of maternal depression. I think one thing to note that this study found was that maternal depression was a predictor of CRP, this longer term chronic inflammation, but not of cortisol levels within the offspring. And I'll post this paper so you can take a closer look at it later. So when we think about one thing that these slides will kind of play out the same, and these slides that talk about measurement are probably something that is really critically important to start thinking about when you're thinking about the biomarker that you're going to measure. That generally we measure CRP in the blood and saliva. Both have been validated. It's conventional CRP, which is acute infection. We'll talk about some of the cutoffs on the next slide. But if, for example, you have a cold or a fever or COVID-19, you are going to have a rapid rise in CRP, and the levels will be incredibly high. There's something that's used in the clinic if you're having, it's called cardiac CRP. It's a measure that's used that allows you to see if somebody's having in a cardiac arrest or cardiac situation. So that's something that's used in the clinic. And then there's high sensitivity CRP. So we're just going to spend a minute here. The high sensitivity CRP is what you're going to be most interested in when you're looking at stress, because you can have lower gradations at the lower cut points of CRP. There's been a number of studies that have used a regular assay for CRP, both in the blood and the saliva. Their markers are not quite as refined as I think they could be. Sometimes you might miss something if it's a conventional CRP. The high sensitivity allows you to analyze the data in a different way. There are many individual assays you can use to look at and get high sensitivity CRP. We're yet to look at an assay that gives you multiple biomarkers at one point in time. They're working on it, but that has not come to fruition. I will say right here that CRP, we do look at it as the longer term cascade effect. There is CRP can be produced locally and immediately. There's an MCRP and a PCRP. So if you're interested in CRP, you're going to want to dig a little bit deeper in looking at what those other biomarkers are. But for practical purposes, the HSCRP are what most people are using and seeing pretty good effects with. Okay, so we talked about the high sensitivity CRP. It gives you a lower limit so you can get the milligrams per liter, could be a little bit lower. When you're looking at CRP or any of the others, you might want to consider, definitely for CRP cutoff criteria, we said that if there's an acute infection, that the response is really high for CRP. So it will be 10 or greater. So you want to, anything that's above 10 is somebody's having an acute reaction to an allergen, or they have a cold or anything like that. From 3 to 10 milligrams per liter, it's a stress-induced response. And anything below 3, we're think of as pretty normal background noise and CRP. The other things that you want to consider, and I would say with most of the biomarkers, some of the other things that you want to consider is that when you're drawing the blood or you're taking a saliva sample, have a corresponding questionnaire. We always do this. When's the last time you had a cold? Are you taking aspirin or some other anti-inflammatory? How often, how much, and for how long? It's a really quick questions that can be asked, but it will impact what the level of the CRP is. Okay, I'm going to move on to interleukin-6. IL-6 is another common one that we assess. And I will say that the ones that I'm showing today and the ones that are most commonly assessed are pretty stable in blood samples and in saliva, and that's one reason why they're so popular. IL-6 will have these effects, pleiotropic effects, and that just means like it happens in one place, so really pretty close to one cell, but then it cascades outwards and have multiple effects in the body. And so that's where CRP starts, and a number of other cytokine or APRs will start. There is, most cells throughout the body will express IL-6. And I think that's another reason why it's so studied, is that it's in the endothelial cells throughout your body. It's in bone cells, the osteoblasts. It's in your sympathetic neurons, so throughout your nerve system. So every cell will have this. And that you could measure it sometimes at the cellular level if you're doing animal studies. But in humans, we generally measure it elsewhere as a system within the system itself. It upregulation of adhesion molecules. So within the endothelium, those are the cells that line like your arteries and veins. And so we can actually put a probe in there and take out from humans some of the adhesion molecules. We can take out the IL-6 to see what's being affected within the arm itself. So it's powerful in the sense that it's in most of the cells. So this is a study in African-American men. Somebody had talked about the Trier social stress test for this particular one. What they're doing is they're inducing stress, and there's multiple ways to do this. For this study, they basically had the men set up for a job interview, and then right after the job interview, they induced more stress by having them take a math test. So that would be pretty stressful for me if I had to do upper level math right after a job interview. And so what they wanted to do was see if somebody had childhood trauma or was currently exposed to community violence, what that would do on their IL-6 levels after this acute stressor. So they're looking at kind of these long-term effects of stress through childhood trauma and community violence, induced by an IL-6 response with this short-term acute stressor that they're putting into place. And what you can see here, and they looked at it in the saliva, IL-6 in the saliva, and what you can see here is that for those who had the most childhood trauma, we have a really substantial acute IL-6 response rate. And the same is true with those with the highest direct exposure to community violence. They have a really, I want to say nice, because it is such a nice curve, but it's like a really good response curve to IL-6. And this is important because as you may have talked about on the cortisol levels, if you have chronic stress, or exposure to chronic stress, that sometimes the cortisol gets blunted, the response rate gets blunted. But this in IL-6 is saying that we're still seeing that response rate. So for the measurement of IL-6, it's often taken in the blood and saliva. Some people have started taking this in sweat, extracting sweat. The considerations is it kind of initiates the process. So you might see it earlier on in a stress response rate, that it is a pro and an anti-inflammatory. IL-6 also will help with tissue repair. And I think that's just keeping it in the back of your mind as you work through these things. And it's often used as an inhibitor or a target to really prevent diseases. So we talked a little bit about cancer. IL-6 will sometimes be a target for cancer prevention because of this cascading effect that it has and the initiation process. So this is really just to show, there was a study, Frada et al. Did a study in 2018. And what I want to show with this slide is the consistency. Well, I guess there's two things that I want to show. The consistency between biomarkers, whether they were taken in the plasma or in the saliva. So if we look at CRP as an example, and all these charts will read the same. This was done looking at test, post-test, pre-test. So this is kind of a rest day where nothing's happening. This is the pre-test and the black. The gray is the pre-test and the black is the post-test. And what you see with CRP is there's really no effect, whether you're measuring it in the plasma or you're measuring it in the saliva. We don't really see any effect between the rest days and the pre and post exam. We didn't really talk about IL-1 beta. It's another common marker. And here what you see is in the plasma and the saliva, we're showing the same effect, that from the rest day before the exam, it is higher among the stress response is higher, but after the exam, it's also, it's higher than the rest day, but it's significantly lower than before the exam. So there's some relief that's happening with IL beta. IL-18, the same thing, we're seeing a similar response. When we look at IL-6, we have a different response where the pre-exam, it is increasing, and then from the post-exam, it continues to increase. And that's true whether you're looking at the plasma or the saliva. So in the pre-exam, it's different than the rest day, and the post-exam, it's higher than the rest day. But post-exam, it continues to increase and is higher than the pre-exam day. These are just to consider the consistency between the plasma and saliva, but also to consider, okay, well, different biomarkers might have different responses based on what the stimulus is or the stressor is. Okay. The last one that we'll cover is TNF-alpha. It's called a master regulator because it has so many impacts on different inflammatory cytokines. It kind of orchestrates the cytokine cascade. And again, that's why it's targeted so much for disease prevention, to either to treat diseases or prevent them. And CVD risk upregulates, and on TNF-alpha upregulates adhesion molecules, and that increases CVD risk. This is looking at the interaction effects of earlier and later life stress. So I think this is another way to think about when you're going to analyze your data and how you're going to analyze your data. This looked at folks who had been abused as children, and then as adults, they're becoming caregivers, and they're either abused or non-abused as caregivers. And it's looking at the TNF-alpha in the, I think this was in blood samples, that the childhood abuse was associated with higher TNF-alpha levels and magnified when it was in caregivers, when the caregivers were also abused versus non-abused. So I think this is just thinking about, well, how do we analyze the data in a way that makes the most sense to tease apart the interaction effects of early versus later stress. So TNF-alpha can be measured in the blood or in the saliva. It can also be measured at kind of the cellular level if one wants to do some of that probing. And the considerations, I think the main consideration for TNF-alpha is that it has these, like cortisol, it has these diurnal rhythms, that it peaks early in the morning and then will kind of flatten out as the day goes on. This is a very busy slide, I know, but it is one thing that I really want to here's my pitch to all of you. If you can do it, please do it. Look at sex differences. We have a number of studies. I don't know, they did a review article of 30 rodent and animal models and human models, and they're really not looking at the sex differences. If you have all women, obviously you can't do that, or if you're looking at all men, you can't do that. But I think that that would be an area that would be good for further research. There's looking at age and adversity. So early childhood adversity increases inflammation across most of these inflammatory biomarkers. And I'll post this so you can see that paper in more detail. I think it's a really good review article to get a sense of what's being measured and how it's impacting the different results, and how do we interpret this both in, I think there's only one animal researcher here that I can tell from your intros, but both in the rodents and humans. Okay, so we're going to do a little bit of summary. I'm going to show you some other data, and hopefully we'll have some time for questions. So what are the key points with cytokine activity? Timing, you want to consider timing. When along the process do you expect to see something? You want to think about the action. Is it going to be local, or is it having kind of this local action, or is it going to impact things further on down the line in the cascade? And then what are the mediators of these? Obesity, and I did it once, or consistent. That might not be the right framework, but what I mean by that is, like, obesity is a consistent mediator. It is, you know, you have belly fat, it's hard to get rid of it, it's going to be around, it's consistently around. So that visceral adiposity, exercise, an acute bout versus consistency. So are you just exercising in a lab and you do one time of exercise? We do a lot of these studies with postmenopausal women and non-exercisers. You know, what's the inflammatory response? And more importantly, if we get them to exercise regularly, can we decrease that initial inflammatory response? Looking at diet or supplement use, we know vitamin D is a really is seen as something that might be able to decrease inflammation, and then again the medications. So what I mentioned mediators here is because I think those are things that you want to measure. You want to try to measure. And I would say weight gain during pregnancy is another thing that you might want to measure. Pre-pregnancy weight is something that you want to measure. Visceral adiposity, if you can. Those are all things that will make a difference when you analyze the data to help you better understand it. For key points for samples, like most blood work, we want to think about it in the fasting state, if you can. That is ideal. But if you're not doing it in the fasting state, then what does it mean to have done it when you did do it? So recording the time and whether people are fasted or not. And that goes for earlier in the day. And if you're not doing it earlier in the day with something like TNF-alpha, trying to do it at the same time of day. So that scheduling can happen. That might make it tricky. And that's certainly true within a person. So you can think about between people or within the same person. So, and these considerations and making them consistent are really important. but even if it's the same person trying to do it at the same time of day for longitudinal studies. With the processing blood samples, the biomarkers that I talked about are pretty stable in the blood, but you want to make sure that if you're collecting blood, it's being processed within 2 hours or so. And then these are the little details, but I think that if you're thinking about trying to do this within blood, there are different, without going into too much information, there are different types of preservatives in the tubes, and that matters. And you can tell because they have different colors. There's the purple tubes and the blue tubes and things like that. So if you're going to collect it on your own, and I would say for your first time around, maybe you want to partner with somebody that does that. And most biomarkers, if you process them and freeze them, they're pretty good for about 4 years in a -AZ freezer, sometimes longer. Okay. For stress research, here are some of the things that we went through, and it's just kind of a highlight of the points we made. Stress during pregnancy, higher inflammation in offspring at age 25 years that you measured at 10, 11, 10, 15, 20, 25. At 25 years, they were still seeing higher inflammation among the offspring with the mothers who were depressed during pregnancy. That there seems to be pretty consistent results, whether you're taking it within plasma or saliva. So again, that gets back to what's your lab infrastructure looks like. Where is the cytokine or APR relative to the cascade, the inflammation cascade? And then early childhood adversity heightens response of adult adversity. And we saw that in 2 studies. Looking at overall response and interaction effects. All right. So that was your quick overview of some of these biomarkers. I'm really going to do a little bit on multiple biomarkers and why I think those indices might do better at understanding and interpreting your results. There is a number of studies that have looked at stress and mortality, stress and disease risk, and also thinking about interventions that could mediate the effect of stress and disease risk. That there's the anti-inflammatory diet, there is physical activity that we spoke about, and we're going to look at some of the studies on diet as well here. So there was a group at NIH, Verandon, that made a simple inflammatory index. I'm not going to go into the details of all of them, but looking at the 15 inflammatory biomarkers in that NF-kappa B mediated pathway, and then looked at 5 chosen for a predictive value, and they took the 5 and they combined it in what they're calling simple inflammatory index and then a sex specific simple inflammatory index. These indices can be created in a number of different ways. I will show you one slide and some of the considerations for that. I think the first thing is, what data do you have and what data do you want to collect? So they combined these 5 into these 2 indices, and here's what they found. They found overall that if they looked at the individual biomarkers, it's very common to log these because they don't have a standard curve. But if they looked at the overall index, the simple index, especially if it was sex specific, it did an overall better prediction at mortality risk with the inflammation phenotypes at 10 years, 1 year, and 2 years. This again is looking at the inflammatory, simple inflammatory index. This is how they calculated it. They weight it, they take the logs of things. I think that is a detail that if you're interested in, I'm happy to talk to you about later how to create those. But for the purposes of this, what you can see is that the simple inflammatory index does a pretty good job thinking about survival rates. These are standard curves that are used in some of the calculations that we do, and that survival rates were decreased depending on how far down, how much inflammation was present. And you'll see a similar thing here with intravenous drug users and survival rates, that the higher the inflammation index score, the lower the chances of survival among IV drug users followed over time. We did an inflammation indices and related that to diet to see how could diet be a mediator and the impact of inflammation. And so this is just to say you have, this is using COVID-19 and looking at how it impacts immune defenses. When you age biologically, you have a weakened immune defense. We know that. And that the recovery time or death is possibilities, that you have a lengthened recovery time if you have a weakened immune system. So what can we do to possibly strengthen that immune system so you reduce your recovery time closer to what we would see in someone who was younger? And that's the yellow line here. So the blue line is somebody who has a strong immune defense, that we know that there happens when biological aging, that defense weakens. Can we get it built up a little bit more so we reflect a curve that's closer to a stronger immune system? And one of the ways we might want to do that is through diet. So we created an inflammation score using the Framingham Heart Study. We looked at 15 biomarkers that they had in the Framingham Heart Study and created a score with z-scores and other values to get an overall pro-inflammatory score. We also created other indices looking at oxidative stress, adhesion molecules, a series of acute phase reactants, and then the top three that we usually see, the CRP, TNF-alpha, and IL-6. And here what I'll show you is just the pro-inflammatory score and what we found related to age. So I'll orient you to this slide. The next couple slides go this way. This is the inflammation score. A higher inflammation score means poorer health. It means a higher inflammation score means higher inflammation. We did this based on age. And then this is kind of a low diet quality, a middle diet quality, and a high diet quality. And this asks the question, if you have a high diet quality, could it really overwrite some of what's happening with inflammation? And what we see here is, regardless of your age, that in fact a higher diet quality lowers your chances of inflammation. And that's true at age 65. We see it. We know that if you're over age 65, it makes sense that you would have more inflammation. We see it again if you're looking at age 50 to 65, we also see that same trajectory. And even at the younger ages, diet has an impact on lowering the inflammation score. I will say that we saw the effect of diet and diet quality on the inflammation score much more strongly than we did on any individual biomarker alone, and nothing at all with CRP. We look at this again, we were kind of interested in this obesity question because we know that a higher obesity state really can impact the inflammation state. And so what you see here is that when it is when you're in obese state, and we measured that by BMI greater than 30, that's a standard way that it's measured in the United States, that there's really no impact of diet, that diet cannot override that obesity. And even in the overweight group, we do see a trajectory with higher diet lowering the inflammation score, but it's not significant. We really don't see the impact of diet on inflammation until we're in normal weight individuals. And this is the Framingham Heart Study. We just do it below 25. There's really no one who's underweight in this study. Okay, the implication of indices in menopause. Again, this just kind of gives you another schematic on CVD risk. It breaks it down a little bit more, thinking about metabolic disorders and metabolic diseases, and what's happening with the, once we have type 2 diabetes risk, which is, again, is on the trajectory to cardiovascular disease. We're going to look at, we're really going to start looking at some of these adhesion molecules and endothelial function. And this is to say that maybe we want to start looking at the inflammatory cytokines or the inflammation biomarkers by where they function within the body. And one way that they function within the body is with endothelial dysfunction, which is a CVD risk factor, so a cardiovascular disease risk factor. And we look specifically at adhesion molecules within the endothelium in the arm for ICAM, VCAM, E-selectin, and P-selectin. And this is why we're interested in this. These are kind of the inflammation biomarkers that are released at the endothelial level, and they really increase the VCAMs, ICAMs, and the other factors that restrict, they vasoconstrict, and they make the vessels sticky. I think that's probably the best way to put it. And this is where you kind of start getting your buildup of plaques and starting to get aggregation of things that block the arteries. And you can see that starting to happen here too. So the inflammation biomarkers are activated. It activates the ICAMs and VCAMs, E-selectin and P-selectin, and it kind of starts a plaque layer. This is talking about the endothelium specific inflammation. And then if you put a probe into the arm, you can actually start measuring the IL-6 and TNF-alpha in humans to see what the relative concentration of those things are. Okay, so we started doing some of this work in menopausal women. And what we found was that for postmenopausal women, inflammation scores related to CVD were associated, the strongest associated, again, like we saw in Framingham, that when we had a inflammatory score that was reliant on adhesion molecules and oxidative stress, that diet made a difference. But it really didn't, we didn't see the difference in diet with individual indices. We did this in postmenopausal women, but then we also compared it to men and premenopausal women. It's often common to do that, especially if you group them by age, because the men will not have estrogen, and premenopausal women will have estrogen. So you just want to see, is it an estrogen effect or not? One of the ways you can do this calculation is similar to allostatic load, which you may or may have spoken about, that you take a number of different pieces of the puzzle. Here it would be different cytokines, and you can group them by allostatic load by the 25th percentile. You can do Z-scores. If you're looking at measures over time, you could look at changes over time. This is getting really to the analysis of those. And I think the main point of this slide is to say there's different ways in which you can analyze the data to get a clearer picture of what's happening. And and this slide just kind of closes it out with saying that inflammation affects all parts of our body, and depending on what you want to look at, there is probably a role of inflammation within those. So that is my, I'll share my last slide. If anybody has any questions, you're welcome to contact me at this email address. Or here's my full address on campus as well. Okay, so I left us a minute to answer any questions. I can stay on longer now or at the end of the next session if anybody has any questions. But that's inflammation in a nutshell, which is pretty quick. Okay, yes, Kęstutis.
You mentioned that you use high sensitivity ELISAs for measuring most of these markers.
Well, for CRP.
For CRP. Okay. How about multiplexing? Have you used that at all, or are
Yes.
they not sensitive enough to pick up any of that?
So multiplexing, and that's what the whole next talk is about, is multiplexing. They, as far as I know, there's no multiplex that has a high sensitivity CRP. I know they've been working on it for a long time. We will analyze anything else. And in fact, we probably throw in CRP when we do our multiplex. But if we really are looking at CRP, we'll do a separate assay.
So just typical 96 well plate, is that how you do it?
Yes.
Okay.
Yeah. Yeah. Any other questions? Okay. Yes. And you know, I know we're on break, so if people want to just take a break, I'm happy to answer your question, Emma. But yeah, go ahead.
I was just going to ask, how do you think about like the kind of cascade of experiencing early adversity and the effects of that on inflammation? Like, do you think of it as early adversity affecting like baseline inflammation, or is it more so the response, like the inflammatory response? Or just curious how you think about that across the life course.
Yeah, it's so we're really thinking about it, and there's multiple frameworks out there that it's really kind of this. There's two ways. One is thinking about it, it's a higher elevated baseline across, and that especially within trauma, the early childhood adversity or some sort of trauma, that there's a heightened response when they're stimulated again. So it's multi-phase, but that would be a really great question to explore more.
Okay, thank you.
Any other questions? Okay, so I'm going to actually let us have a break. We'll come back at 2 o'clock for our next talk.